Again, good afternoon, good morning, good afternoon, and welcome to those who may be watching the recording. My name is Stephanie Lewis. I will serve as your moderator today, and welcome to another National Institute for Congestion Reduction webinar. Today's topic is prioritized vehicle scheduling and general conflict area under connected and automated environment. It is my pleasure to introduce our presenter today, Xiaoping Li is currently a professor in the Department of Civil and Environmental Engineering and an affiliate in the Department of Electrical and Computer Engineering at the University of Wisconsin Madison. He previously served as the director of NICER, and he is a recipient of the National Science Foundation Career Award. So, with that, it is my pleasure to introduce Shaw. So, Shaw, go ahead and take it away.
Stephanie, thank you very much. Hi, everyone in the audience, and it's my great pleasure and honor to present some of our nicer work today here. So, yeah, since I moved to UW-Madison and stepped down from the administrative work with nicer, I'm still continuing working on the research topics related to vehicle scheduling, transit priority, in the context of connected automated and vehicles environment. So I'm going to share with you some of our work during this during these years, and so like so this is a starting of my first slide. Again, this is going to be the same title, and I want to say that we have a total of 3 projects within the nicer community, and I'm going to talk about the first 2 and then also discuss a little bit about the third. That is going to be concluded next year sometime. So the first 2 projects are related to transit priority, and so essentially we want to look into this problem in a general perspective. We want to the priorities or the or preemption, all these kind of operations essentially are giving vehicles the the right of way prior to the other vehicles at so-called traffic conflict areas, like intersections, like merging roadways, work zones. So when we say transit priority, specifically, it refers to the giving the rights of way to the transit at a higher priority compared to other vehicles. So eventually, we're dealing with infrastructure facilities like where vehicles from different approaches have conflicts, and we have to schedule them to certain kind of like alternating rights of way over the time and have the vehicles to pass or traverse these conflict points in an optimal manner. So what's the problem of such vehicle scheduling problem? Such vehicle scheduling problems. What are the issues that we may face? So when we say these conflict points, if they're not very efficient, then that means the schedules of these vehicles or the sequences of these vehicles passing the conflict points are not optimal. You can consider all these different facilities like stop sign, yield, intersection, and signal timing. It's like you have so many different alternatives and parameters to control, and if you are not designing them properly, then the intersection may not have a good capacity, and they may not give the proper priority to transit. On the other hand, we may also concern the fuel consumption, energy, and emissions. So that also is related to the stop and go pattern of these conflict points. For example, at signalized intersections, you have to stop some approaches to let other approaches go. So that will inevitably form stop and go traffic patterns, which is going to bring excessive fuel consumption and uh, massive emissions as well. So transit priority is just like one facet of the problem here at the here in the problem of vehicle scheduling at the intersection. So essentially, we're gonna schedule these vehicles to pass the intersections so that the overall road users receive the highest benefits in terms of overall mobility. And the reason that we give the transit priority is that transit has a higher ridership than other vehicles, and maybe so I think the rationale description would be giving the transit a higher priority, for example, proportional to the number of riders within the transit vehicles in this case. So the problems we're going to investigate is in a relatively like high-tech scenario with the connected and automated vehicles. So in this scenario, all the vehicles are connected and automated so that you have the full control of the system. And I think you have already seen the animation here that is a fun version about what happens in the future if the vehicles are all automated. And it's a little bit exaggerating since you see people walk across them. But if I would not dare to walk across an intersection like that. But if you take away the pedestrians and, so if we can really nicely arrange the vehicles in this manner and to have them perfectly scheduled that they do not need to stop at the intersection, that will give that will and have the maximum mobility and minimum environmental impact, as well as good assurance of the safety. And so in this kind of like problems, when you have vehicles are all controllable and you can give them like a slot of time for them to pass the intersection, then you can then we're going to investigate how we're going to treat transit uh, and so basically we're just to view it as a vehicle as with a higher weight compared to other vehicles, and we put this into a more general framework where there are all kinds of different vehicles with different weights, and we want to sort of optimize the overall system performance considering the different weights of the different vehicles. So we have been looking into the methodological literature of relevant problems, particularly pertaining to vehicle scheduling. And there are decentralized approaches and centralized approaches. There are many relevant studies and developments. And the gap we identified is there is no CIV-based centralized optimization problem that coordinates vehicles at a general conflict point with heterogeneous time values and headways. So when we say the heterogeneous time values, it's because transit would have a much higher ridership than a passenger car, and that way, I would view the delay to a transit, the cost of delay to a transit would be a multiple times more than that of passenger car, for example, maybe proportion to their riderships. Note that this is in a relatively ideal scenario setting where we have the full information. We know all the riderships of all these vehicles and we know all these weights. I mean, the assumptions might be strong, but as a first study that shows you the potential of the system, if we get all the information ready, that is still possible if we continue to enhance our infrastructure and the sensing and facilities, devices. including connected vehicles and automated vehicles capabilities, and we will be there. So we think this study is still meaningful. And also we have rigorous and a general model formulations that can be adapted for all kinds of different applications, including transit priority, but not limited to that. So the problem description, I would say, we consider general like conflict area that could have different approaches, more than two approaches, could be three or four. They have to pass a traffic conflict point. Because you have multiple approaches, you have to give each approach a certain time slot to have them pass. All right, so it's a generalization of the conflict points we've seen, like signalized intersections. It's like you have signals to allocate the time slots to different approaches, or stop sign that means okay, first to come, first to served, or yield sign that means certain approaches have priorities over other approaches. And then the overall problem is just like, suppose you're given all these vehicles and where they are at. That's what you have here. And you want to devise a sequence for these vehicles to pass the traffic conflict points based on the characteristics of the intersection. Let's say, and in this case, we would assume this is like a signalized intersection where we have the control of which approach to pass this traffic conflict point. Then we can have all these vehicles to pass that traffic conflict points. And the overall problem is how to find the optimal vehicle scheduling or the sequences of these vehicles to pass the intersection. We consider multiple approaches at the conflict area. We consider different priorities or value of time. And that reflects the transitive priority. And we may also consider heterogeneous headways because some of the vehicles, bigger vehicles, particularly like transit, they may have bigger gaps, headway gaps. So it's just like we have this generalized design, and it works for passenger car traffic, pure passenger car traffic, if you're just to give all these vehicles the same weight to the same headways, but it also allows us to incorporate the transit priority if we give them different weights. Okay, so we assume that systems fully connected environment. All these vehicles. All these vehicles and information in real time, and their history. And overtaking from one approach is not allowed. So maybe one approach is just a single lane. And extremely congested traffic is not considered. We consider moderately congested traffic where CAVs travel within the control areas at a free flow speed. So no queue is it's not too much oversaturated. So you can still have the vehicles pass the intersections without excessive queuing. And we want to maximize traffic throughput at the conflict area. All these vehicles are all connected, automated, so they're CAVs. So all CAVs pass the conflict area with free flow speed. So that's a essence of the non-stop intersection design. We can control these vehicles properly to have them accelerate and pass the intersection at the high speed to improve its efficiency. So here's a model formulation. I don't want to talk too much about the mass, but I just want to give you some flavor. So objective is to minimize the delay cost of all vehicles. And you may ask, wow, this is a transit priority, but why do you want to delay the cost for all vehicles? I would say transit priority is essentially, in general, a trade-off between transit delay and other vehicles delay. Let's say we do not need to give the transit absolute priority over all circumstances. You have to balance the delays between a transit and other vehicles. For example, if you have a transit vehicle that has 20 passengers on it, all right, of course that is worth the delay, 1 second delay of that transit is worth 20 seconds delay to a passenger vehicle with only one rider. But at the same time, if that transit only has 3 riders on it, and if you're giving the transit priority, but the cost is you're going to delay the conflict approaches vehicles by an extra 100 seconds. You know, let's say you gain let's say 2 seconds priority from your transit with 3 passengers, but you're going to lose like 100 seconds late for all the other road users. It might not be the best decision. So instead of viewing transit or particular mode separately and give that absolute privilege, I would say, we in this kind of environment, in the ideal connected automated vehicle environment, we just want to give them a weight. So that's what this UK here. All right. So each vehicle K here has a weight of UK, and that's probably the best representation of that system overall delay. You give them like the weights of their delay, and that way transit and all other vehicles can be incorporated. Of course, there may be some other cases like you say emergency vehicles that may have that may have absolute higher priority, and then you can give a very large UK this value, this weight to for that kind of vehicles. I just want to say we consider the system in a holistic manners, incorporated different weights for vehicles with priorities. And there are other some constraints. The first constraint is basically means where the first vehicle's condition, and the following constraints are like for the following vehicles, they have the earliest arrival time, like the safe headways between vehicles. And the third constraints are here we have two figures, between every 2 consecutive vehicles passing the intersection, you have 2 cases. The figure on the left shows switching. It's like from one approach to switching to another approach. All right, that will normally have a longer headway. I would represent that as HS, which is from switching from one approach to another approach. The other type of headways is the following headway. It's like like the figure on the right, you have 2 vehicles following each other, passing the in the same approach, passing the conflict area. That's going to have a relatively small headway. That is represented by HF. So based on whether these 2 consecutive vehicles are from the same approach or not, you can actually you're going to have like different headway types. And so overall, so your optimizations decide the vehicle sequences, which approaches need to pass first, so that you can minimize the overall system delay weighted by the vehicle's priorities. So now we have the formulation, and we just want to look into the solution algorithms. And because this is real-time operations, maybe the solution algorithms efficiency is also relevant. So, I mean, it's if you're just looking to the formulation, it's a very complicated scheduling problem. If you know that scheduling is in general an NP hard problem, that solution time could increase exponentially as the problem scale increases. So we came up with some customized algorithms to expedite the solution time. And we also have some heuristic methods to approximate the optimal solution to get them a near optimal solution in almost no time. And also we want to reduce the problem size by platooning the vehicles together, basically cluster the vehicles into platoons, so into longer vehicles. So we have a fewer number of vehicles. So the first 2 solutions would be the year 1 project that is coming up with the corresponding algorithms to expedite the solution approach, and that reducing the problem size, the year 2 project. And I'm gonna explain these 2 years of projects outcomes here, particularly the algorithms, in the following slides. So first, I'm going to introduce the year 1 solution 1. So Solution one is expediting the solution time. So basically, what we do is we try the branch and bond methods. So, and the branch and bond is, we know it's like a way to solve this kind of a scheduling problem. It's for, I'm not going to go too deep in the method. It's basically for one variable, it has, for one variable, which is the vehicles to go or not to go. Like you can branch out the decisions to this vehicle needs to go before this time or after this time, right? So of course that the challenge of this branch and bond is that you have so many vehicles to schedule. Each one's going to branch to have two branches, and then you're going to have a very large number of branches. So how do we really make that branch efficient? So what we did is first we came up with some lower bound and an upper bound of the branches so that we don't need to go to meaningless branches that exceeds these bounds, right? The lower bound would be first in and first out. Consider the homogeneous case. It's a suboptimal solution. It's just like a stop sign, right? That's that works, but that may not be optimal. So, and what you can do is minimum safety headway, time headway among all vehicles, and assume the value of time for every vehicle equals to the same value and no switching time anyway. So with that, you can come up with lower bound. And upper bound is a fast heuristic method to generate a feasible solution. That is going to be a feasible solution. So we use fast heuristic. We can generate a solution that will give you a suboptimal value. Whereas the lower bound up here is actually, the optimal solution will not. The delay will be always above this lower bound. So we have these two bounds, and then with that, then we can come up with a structure of node, how we branch and bound. Okay, I'll be quick here. So we basically have used a vector to represent a node. The first n values will be the number of passed vehicles from each approach, and then the following two values, the last passed vehicles are approach index from which approach, and last passed vehicles departure time. All right, and based on that, we add these value. So I want to say, if you, what we can branch is to branch these n's, and that's going to give you the corresponding p and t's values. But of course, every time if you branch an n, that's going to double the number of nodes. So there will be so many nodes if we do not have extra treatment. So that's why we introduced those called valid cuts. These are some conditions that regulates the branch of these vehicle sequences. So for example, that I'm not going to explain the mass detail. The basic idea is that vehicles have from one approach cannot overtake from each other. Okay, one vehicle, that from one approach, the downstream vehicle will always pass the intersection um, before the following vehicles passing the intersection. They have certain headways like following headway, switching headway. We can consider all these conditions to add certain valid cuts. That is what the cuts do would be just reducing the number of nodes. You don't have to always branch. For some branches, you're going to cut them in because they're meaningless to explore. So here are some of the results you've seen from we did some tests, and maybe you can just so we compare the number of nodes we explored from 3 different methods. The first is branch and bond algorithm without the valid cuts. The second is Ruby, which is a commercial software to solve this problem. The third method is our proposed method is branch and bound with a valid cut. And so these graphs showed like so on the left they show like 2 approach conflict area with different number of CAVs, and you can see actually B and B and the vertical axis is number of nodes explored. You see, if we add the value cut, which is the blue curve shows, it's going to much reduce the number of nodes explored. And whereas if you don't add value cuts, you have to explore a lot more nodes. That's going to increase the computational time and bring down the model efficiency. And on the right, we showed compared for all these three methods, and we see that branch and bound plus value cuts. That is the uh, dotted line in the bottom explores much lower number of nodes compared to other methods. That means, okay, we don't need that probably indicates our method has the best efficiency. And we conducted some numerical examples and we show the results. Here are the solution times and also the gaps. And we see our branch and bound with the valid cut B and B-V has the minimum solution time and the minimum like optimality gap. That means that our methods works well. And in terms of computational time, our method, okay, for two approaches, it's always less than 0.4 seconds. For three approaches, it may increases as the number of vehicles increases. It can get to 167 seconds, which may not be feasible for real-time applications, and there will be still need some room to improve the algorithm, but at least it much outperforms the other methods that are available off the shelf. Compare the group B, the first column, the branch and bound without valid cut. So that means this is a really good solution. And then we can apply this method to realistic problem that has continuous traffic flow. So what you can do is just you can solve this problem in a rolling time horizon. For example, you're going to divide that. Let's just look at the figure on the left. The figure B, let's say figure B here. Step one is like you're going to construct two areas. What we show here would be like the lower portion is the segment is a road segment of one approach, and upper portion is the conflict segment approach. I just rotate, let's say, for example, I'm going to rotate this roadway, the eastbound. I'm going to rotate that eastbound road to make it more like a southbound, and then we plot out the vehicle trajectories. So the upper trajectories are actually the eastbound trajectories, and lower trajectories here are the northbound trajectories. So this way we can plot out the vehicle trajectories of the two constant approaches in the same plane. So we actually, for each approach, if you notice, we divide the roadway areas into two areas. The first is L1M, for example, that is for approach 1. That is northbound traffic, I believe. That this L1M is maneuver area, we call it, and M1C is called the control area. So what we do is at a certain time, let's say, we're not gonna touch anything about the trajectories or vehicles within the maneuver areas, and these vehicle trajectories will be already solved, and just to follow the trajectory decided by the previous rolling previous time window. And what we need to do is to optimize the trajectories within this control area from both approaches. So we do the optimization, and you can see this vehicle trajectories will be changed into the pattern in step 2, graph C, and you can see they're going to be the optimized trajectory within the control area. L1C will follow the trajectories shown in the figure C. And then this is done for one cycle, and we're going to move the window to the next window as from the red vertical curve to the green vertical curve in step 3, figure D here. And then after this time window, we still keep the vehicles that are optimized from the previous step the same from the from the previous time window the same. We will only need to optimize the trajectories in the of the vehicles right now at the green vertical line within this control area. So we can do this uh, repeatedly so that we will optimize all those trajectories consecutively with the method. So here are the solutions results. We plot out the vehicle trajectories first for our method. That is this figure, top right figure, proposed individual-based control PC, and we see vehicles form relatively small platoons. And then we have reservation-based control. That is more of the um, uh, it's more like a vehicle arrive first to serve. That is shown in figure lower left figure. And then we have adaptive signal control. So we use adaptive signal, um, uh, classic adaptive signal timing method to control the vehicles. This is ASC, and we compare the throughput and total delay, and we found that the proposed control has the best total performance. So for this solution 1, the conclusion is it's a new and efficient vehicle scheduling model considering transit priority. And we see the branch and bond with valid cuts actually beats all other solutions. And individual-based vehicle scheduling result into less total delay and fuel consumption compared to reservation-based vehicle scheduling. We didn't show fuel consumption, but because of the vehicle trajectory smoothing, we did have less fuel consumption. Okay, now I'm going to quickly go through the year 1 solution 2, that is how to reduce this problem size. So this is inspired the concept of platooning. Vehicle platooning refers to a closely following mechanism of vehicles in a coordinated way without having the mechanical linkage while maintaining a safe distance. So it has lots of advantages, like improved aerodynamics, smaller headway, and higher capacity, less accident. And also we can put the transit priority in the context of the platooning, can sort of combine the transit priority with the other vehicles as platoon, so we can handle them as one vehicle. And this is going to have resulting enhanced performance for public transit, and we can optimize the priority for transit vehicles in the same manner, just like we assign it appropriate weight. So here, what we want to do is why not we just so in the problems, vehicles do not have to like using CV to platoon each other very closely, but you can view, and it doesn't have to be like 0.5 second headway, but you can just have the vehicles following each other with 2, let's say, second headway, as we've faced a lot in the arterial traffic, right? Even if you have that, but the concept is we can group vehicles that are close to each other in platoons. For example, in this conflict point problem, you have a total of like 12 vehicles, right? You have to control them individually. But instead, if you group them into different platoons like theta 1, theta 2, and theta 3, and so on and so forth, you're only going to have like 5. So each vehicles close to each other can be grouped in one platoon. That means they need to be synchronized and they move together, right? If that's the case, and you're basically combining shorter vehicles into longer vehicles, or reducing the number of vehicles in this control, And that's going to much reduce the problem size and improve the solution efficiency. Okay, so as the number of n, like the start initially, you may have like n controlled vehicles, but as you do some certain kind of platooning, let's say if the headway is less than the threshold, you platoon them together, you're going to have much less vehicles to push this n in the graph to MP, and that is going to much reduce the computation time for schedule the problem because you have much less or fewer number of units to schedule. And so again, let's say we can translate this. We want to compare the solution of the reduce the problem and original problem. So let's say again, our problem is to decide the optimal passing sequences of the vehicles, right? For the original problem, we're going to use script S on the top to define a set of all possible passing sequences of vehicles. And after you consolidate the vehicles using the platooning, you're going to use a script S super P to show the set of all possible passing sequences when the platoon rule is applied. All right. And from that, you can find the optimal solution S star. That is for original sequence. That's going to be the best sequence. And also you have platoon optimal solution. That is the optimal solution given the vehicles are platoon in this way. You cannot separate the vehicles that are close to each other, right? And because of the platooning, you may lose some optimality because you cut off some possibilities of separating vehicles from the same platoon. So there will be a difference between the two solutions in terms of their travel time delay. The platoon optimal solution will always give you a higher delay than optimal solution S star, and there is going to be a gap G, let's say. And we look into the gap G, and we want to say whether this kind of we can find one platoon method that much reduces the problem time, but does not bring a super large gap G. And if it results a small gap, that means okay, platoon solution is the same, similar to the or near optimal to the original solution. Then that means okay, bingo, we could just platoon the vehicle together, right? So we'll look into this gap, and basically, and we want to look into the upper limit of the gap. We do some analysis, and we look into the upper limit of the gap, and we found that actually, we changed the values of them, and so that in this figure that we show the gaps across two variables. The x-axis variable is delta. That is a platooning threshold. That is how, for example, this is I think threshold is here. All right, headway between these two vehicles. If you have delta is that if ever you look at every pair of vehicles, if the headway is less than delta, you can platoon them together. That's one variable, x-axis, and also the platoon size that you don't want to, you limit to the longest platoon size, right? And you can see the lower right corner of this graph has relatively large gap values, and that means higher threshold theta and lower platooning size. And so the case showed that we should avoid the platoon size is small and the platoon threshold is large, which leads to a great gap. This can be simplified as a guide to vehicle platooning. So we want to have theta greater than or equal to sigma minus 5. We want to have the platoon size large, while in relation to the to the delta, the platoon headway threshold. So we also look into expected number of platoons over vehicle density and platoon threshold. a number of platoons, and we look into their patterns. And eventually we came up with some criteria. The first criteria is going to be just headway between the vehicles less than delta. And we also added some other criteria like current headway of one platoon is total headway, cumulative headway, I would say, is less than k times delta. K is the parameter. And the number of vehicles in one platoon is less than delta minus 5. So basically we have all these criteria and we can apply them. And we come up with 3 different scenarios of the solutions. The first is no platooning. That is the original solution. That is the solution we obtained from the solution 1. And the second is critical headway platooning. We'll only use the first criteria to platoon. We just platoon all vehicles that has a headway is less than delta altogether, regardless of the length, cumulative headway, or the number of vehicles in one platoon. The third is a PP, proposed platooning method, that is to use platooning, including all these criteria 1, 2, 3. And we found that here are the results. Some of the results. So the figure on the left is the number of platoons versus the number of the platoon threshold. And you can see that as the platoon threshold increases, both CHP and the PP will much reduce the number of platoons. That's going to much reduce the problem size. On the right is vehicle density over number of platoons. Of course, higher the vehicle density, you're going to have the fewer vehicles because vehicles will be likely to platoon together. And we see that CHP has the lowest number of platoons. PP here still has significant reductions, but not as much as the CHP, because you have other criteria. You may not have excessive long platoons, but it has an advantage. So with this, you see actually the original solution. If you solve the problem, original solution is going to be the highest. The CHP is going to have the lowest solution time, and the PP is only slightly higher than the CHP. So PP is going to be not as efficient as CHP, but close, and it's much more efficient than MP, the benchmark. Now we look into the average vehicle delay, and we see that the PP is close to the MP is actually the delay we want to have, right? MP is actually the black curve in the bottom, and we see when threshold the delta value is low and the vehicle density is relatively actually across all vehicle densities, the proposed method, that is blue curve, is relatively close to the MP, which is the optimal value, right? That means, okay, so the proposed method, although it sacrifices slightly the computational time compared to CHP, but it improves the problem solution optimality. The solution of PP is closer to the MP solution, that is the original solution value without platooning. So the conclusion is like on top of solution 1, solution 2 proposed the platooning method, which helps generate a real-time vehicle scheduling plan without much loss of solution optimality. We can combine the solutions 1 and 2 and combine our vehicle scheduling approaches at individual conflict points with the city-level control methods. For example, that third year, what we're going to look into is cordon control. So this is the current work, actually. I would say ongoing work instead of future work. So basically, instead of just looking at one facility, one conflict point, we look into an urban area, and we have coordinate metering rows for present day and future cities. We want to model We build a model to calculate the total travel cost of the urban road networks, emphasizing transit priority. The total travel cost consists of two parts, namely energy consumption and delay, without adjusting um, with adjustments favoring public transit vehicles based on the waiting schedule, the scheme that we developed. And task two is evaluation, is to evaluate the impact of CAV velocity variations in the urban network on the total travel costs of the urban networks. Because we may have the flexibility to adjust the CAV velocity based on the urban overall network conditions. This is to minimize the transit delays as well as encourage public transportation use. So here is the list of the work that we need to do for the coordinate metering rules. That is what we're working on. So in task one, we're going to build the road network and into the cells so we can take advantage of cell transmission models. We're going to study the spatial temporal evolution of vehicles and impacts the impact of changes in CAV speed on the spatial temporal evolution. Look into the impact of changes in CAV speeds on energy consumption and the mobility of cities' roadway networks. We calculate and verify the energy consumption, and we're going to utilize some of the tools such as Argonne National Lab, which we have with whom we have quite some collaborations on other projects as well. So maybe we can conduct a case study after task one, for example, using the Madison roadway network. We just this figure shows a scheme about how to separate the area into cells so that we can analyze this network in a macroscopic manner. And so we're in the middle of this project, and we hope to share more results with you in the next year. So with this, I want to thank all of you for your patience, and I'll be happy to answer any questions if you have any.
Thank you so much, Shaw, for all of the great information. I'll just remind everybody you can use the Q&A box in the bottom right-hand corner of your screen to ask any questions. And Shaw, it does look like we have a couple of questions already submitted in the Q&A box. It says, how would CV and AV help with the model application?
Okay, sure. So, yeah, so that's for CV and AV. So we're considering a very ideal scenario where you have all these vehicles information. You can control the vehicles in a centralized manner, or you can use some mechanism to influence their trajectories. So, and that only holds when we have CVs prevailing and the vehicles have certain automation so they can adjust their trajectories. So these studies relevant to CV and AV technologies, and in the current setting, if the vehicles do not have CV and AV, we do not have the vehicles accurate locations, and we cannot control these vehicles. It's going to be difficult to apply the models to actual control.
Great. And then the next question comes in and says, does this proposed model give priority to transit or also consider other road users?
Yes, like I explained in the formulation, it considers transit and give it a priority as a weight, but it also considers the other road users. Ultimately, we're gonna improve the overall traffic performance in a more of like a efficient and equitable manner. We want to give the transit priorities to a certain level that is commensurate to their ridership, but it's not like we're gonna stop all the traffic and just to have one low ridership transit bus to pass.
Okay, great. And final question comes in, how to apply the complex mathematic models in transit operations practice?
Yes, it's the current practice is going to be a little bit challenging to apply because we don't have such information. But actually, these application models, if you adapt to them, if you just to simplify them, you can take off the trajectory optimization. You can easily adapt that as a signal timing control method. So so with limited information, like even if we don't have individual vehicles information, we have the traffic flow demand, with certain sensors that we have like loop detectors and other sensors, right? So for some of the transit buses, they have communication like connected vehicles or some kind of radio communications. With that data, you can still use a light version of this model. We'll adapt it and to uh, actually can apply the model still to the current practice. And so some of these I think many of the transit buses have the automatic passenger counter. With that, you can count the number of riders on board, and that's going to give you the weights that we need. And with that, we just need to have transit operators and traffic managers and centers to work together to use the transit information and other road users information to improve the traffic signal control, to give them transit bus priorities while also considering the needs of other road users.
Okay, another question says, in the current scenario of lack of extensive vehicle communication among all vehicles, what are the application suggestions for current platooning mode?
So I'm trying to understand what are the application suggestions. So we do not have the communications, right? So actually the platooning here is just a way to process the vehicles. It doesn't require like connected vehicle platooning to reduce the headways, as I explained earlier. So the vehicles, it's just like, in your model, remember, when we view the roadway traffic management, when we view the road, a road segment, right, in the context of the traffic operations, we can, in the finest way, we can represent that road with a collection of individual vehicles. Each vehicle gives you the detailed location, speed, and very refined information about the vehicle trajectories. On the other hand, you can just describe the road segment with aggregated information like traffic density, traffic flow rate, average speed, right? So the platoon is just like an intermediate process or intermediate representation of the road segment. It's not a presentation as detailed as individual vehicles because you cluster vehicles close to each other into the same platoon. It is not, but it captures a lot more variabilities and local dynamics compared to the overall aggregated the traffic like like macroscopic traffic representation, like traffic density, flow rate, because you still have the platoons separated in a space, and you can still visualize the shockwave propagation and other microscopic traffic properties compared to the macroscopic traffic flow. So again, this is a way to model the roadway, just to model the road vehicles, and in a macroscopic traffic manner or microscopic vehicle manner. It's actually somewhere in between. I would say like mesoscopic process, right? So it's independent about whether these vehicles can communicate or not. It's just like a method to process and represent the road segments of the study.
Okay, Shaw, thank you so much. I'm going to open up the evaluation for each of you on your end. Please take a few minutes to complete that evaluation, as the feedback provided is not only important to Shaw, but the entire NICER webcast series. So on behalf of the staff of NICER, the National Institute for Congestion Reduction, thank you so much for attending today's webinar. And we will see you in 2024, not in 2023. Thank you so much and have a great rest of your day. Bye, everybody.
Bye bye. Thank you.
Bye, Shaw. Thank you.